We have already seen that the real numbers are uncountable. That makes them very difficult to compute with many times. Fortunately, for all real world applications, this uncountability is not such a big deal because you can always approximate a real number by rational numbers. This phenomenon is known as density. It will be more clear why it is called density when we reach the chapter on topology, where I make precise what density is. But nevertheless, the statement I'm about to state, the theorem I'm about to state, can be justifiably christened as density. So, theorem, density of rationals and irrationals. What this theorem says is the following. Let a comma b be two distinct real numbers. Then we can find a rational number q in AB and an irrational number C in AB. Proof. Okay, we will first find Q. Okay. Now we can assume both A and B are irrational. Please pause the video and think about why we can make this assumption in this case. Hope you figured out that if both either A or B is rational, then you can just choose that to be the required rational number Q. Okay. Further, we can assume both A comma B greater than 0. I leave it to you to check what would happen in the other possibilities for A and B. I will just tackle this case. It really makes no difference. Now let n naught be the largest natural number such that n naught is strictly less than A. Okay. In other words, A is an element of the closed interval n naught comma n naught plus 1. Okay. Now there are two possibilities. If B is greater than n naught plus 1, then n naught plus 1 works. Okay, because n naught plus 1 is greater than or equal to A. In fact, it's got to be greater than A because we already assume that A is irrational and it's less than B. So we have found a natural number that lies in between A and B, so we are done. So we can assume that B is not an element of n naught comma n naught plus 1. We can make this assumption. Okay. Now choose m in the natural numbers such that 1 by m less than b minus a by 2. Okay. And let k be the largest natural number, again non-negative. This is not just a non-negative integer. Let me just make that precise. Non-negative integer negative integer such that n naught plus k by m is less than a. So a lot of confusing things have happened. So let's draw a picture to make sense of what is going on. So we have the points A and B. We know that n naught is here. Okay. And under our hypothesis, n naught plus 1 is here. Okay. N naught plus 1 exceeds B. Okay. Now what we have done is we have chosen B minus A by 2. That's exactly half this length. That's exactly half this length. And then we are choosing a natural number so large that 1 by m, the size of 1 by m is less than half the size of this interval AB. Okay. Then what we are doing is, starting from n naught, we are first going through n naught plus 1 by m, then we are going to n naught plus 2 by m, so on and so forth, and we are finding the largest integer such that n naught plus k by m is less than a. Okay. There will always be such an integer simply because n naught is less than a. N naught plus 1 by m could exceed a, in which case the choice of k would be just 0. Eventually, when k exceeds m, you get n naught plus 1, right? When k is m, you get n naught plus 1, which certainly exceeds a. So at some integer, it has to be the largest integer such that n naught plus k by m less than a. There will always be such an integer. Okay. Now, n naught, we know that n naught plus k by m is less than a. That means n naught plus k plus 1 by m will necessarily have to belong to AB. Okay. Why is this the case? Well, because n naught plus k by m is less than a, 1 by m is less than b minus a by 2. So adding b minus a by 2 to something less than a cannot exceed b, simply because the length of the interval AB is b minus a and 1 by m is less than b minus a by 2. Okay. Clearly this is a rational number by construction. The trick of this proof is rather simple. By now we are experts in trapping points in between some intervals. All we do is we trap the point A between n naught and n naught plus 1. Once having trapped that, what we did is we just essentially put a scale in between n naught and n plus 1, then made the rulings in the scale so small that we can literally mark off a point that lies in the interval AB. That's all we have done. Okay. Now, what about the irrational case? That is even simpler. We may assume that neither A or B is irrational. Neither A or B is irrational. Okay, for the same reasons that we made as analogous assumption. Then C, which is defined to be a plus b by root 2, works. Okay. Why? I leave it to you to check why this works. It's rather straightforward. So this concludes the lectures for this week. We have seen quite a lot of properties of the real numbers. Next week we will begin sequences. This is a course on real analysis, and you have just watched the module on density of rationals and irrationals.